get to the answer to the eigenstate question first. That is, can the raising and lowering operators have eigenstates? So what we are trying to do is find the lowering operator eigenstate, a state denoted ket alpha, on which the lowering operator A acts, and you get alpha times ket alpha, a number alpha times ket alpha. Well, we know that the harmonic oscillator energy eigenstates, ket0, ket1, ket2, etc., the number eigenstates that we have been just talking about, they form a complete set. That means you can expand any state with some coefficients A0, A1, A2 in terms of this ket0, ket1, ket2, etc. This is, of course, in general, an infinite expansion. And if ket alpha is to be normalized, then A0 square, mod square plus A1, mod square plus A2, mod square, etc., this sum has to be 1. We will worry about normalization later. Let's just first take a look at what happens when you take this state ket alpha and apply A on it. Well, A being a linear operator ignores these coefficients and goes and hits the kets. So you have A0 on which is skipped over, and A acts on the ket 0, AX on the ket 1, AX on the ket 2, and so on. And just by using the fact that A acting on ket 0 is 0 times 0, A acting on ket 1 is square root of 1 times ket 1, A acting on ket 2 is square root of 2 times ket 1, sorry, A acting on ket 1 is square root of 1 times ket 0, A acting on ket 2 is square root of 2 times ket 1, and so on. We get this, which can be written down in this form, in this infinite sum form. Now, what we are demanding is that this particular ket that we have found out, A1 square root 1, ket 0, etc., must be alpha times this. That is the original ket alpha. Now, the only way that can happen is that the ket 0 coefficient of A acting on ket alpha must match the ket 0 coefficient of alpha times the number alpha, and so on. So this can only happen if you just keep on matching the coefficients of the various basis kets here. A1 times root 1 has to be alpha A0, A2 times root 2 has to be alpha A1, A3 times root 3 has to be alpha A2, and so on. In general, An times root 10 has to be alpha An minus 1. And what that means, if you solve this, it's pretty simple, that An has to be alpha raised to n by square root of n factorial times A0. So we have managed to figure out all the coefficients, A1, A2, A3, all the way up to A infinity, or An for any n, in terms of the one coefficient A0. And that means we have found our eigenket. The ket alpha is this overall A0 times this infinite sum, alpha to the n by root n factorial ket n. This is an infinite sum, but of course, in practice, we need only go up to some sufficiently large n so that this 1 by root n factorial in the denominator will cut everything down. We can normalize A0. Again, that's a very simple calculation. I'm just going to skip over that for want of time. But once you normalize this, it's a pretty straightforward summation. And okay, I have the privilege of addressing a few students, I expect, so I'm going to leave that as an exercise for them. The normalized ket alpha is simply this same sum. It is above minus alpha mod square over 2. That's the normalizing factor. Now, this state is called a coherent state. So we have met the hero of our talk rather late, midway into the talk. An eigenstate of the lowering operator belonging to the eigenvalue alpha is called a coherent state. Why is this called a coherent state? We will get a glimpse of that at the end of this lecture. For the time being, let's just take that as nomenclature. The eigenvalue alpha can be any complex number. Of course, all of you know that for Hermitian operators, the eigenvalues can only be real, but A is not. The lowering operator is not Hermitian, and its eigenvalue can be any complex number whatsoever. Now, quickly, for those more familiar with the position picture, the operator A in the abstract form looks like this, but I can always replace the operator in the position picture by h cross over I ddx. So in the position picture, it takes the form given by this. So if you want to find out the eigenvalue or eigenvector for this operator A or an eigenfunction in the position picture, all you have to do is solve this simple differential equation. And despite the fact that it looks a bit complicated because of these m omega by h cross factors, it's really a very, very simple differential equation. It's a first order linear differential equation. And just by changing the variable to xi0 just to make the equation a bit more compact, the equation simply becomes this. D psi alpha dx is a constant times x minus xi0 times psi alpha. And this can be immediately solved by simply a host of methods. One of them would be just divide the whole thing by psi alpha and multiply by dx and integrate. And you get this solution. Now, this should be a very, very familiar solution to most of you. If you leave out the xi naught, and this, of course, is a normalized version of that. And I'm pretty sure most of you can recognize that if you leave out the xi naught, what you get is exactly the ground state wave function for a harmonic oscillator. So even the ground state wave function happens to be a state corresponding to xi naught equal to 0, that is alpha equal to 0. And what we have seen here is that the wave function for this coherent state essentially the displaced ground state. X has been shifted to x minus xi0. So the center is no longer at the origin. The peak is no longer the origin for the wave function. The peak is displaced to a different point. Now, a natural question would be, what about the raising operator? Can we find an eigenstate for that? Can we find a state beta such that A dagger acting on beta is beta, the number times ket beta? And the answer to that is simple. We just try whatever we did right a while ago. We expand beta into harmonic oscillator eigenstates. Divide with 1, ket 1. This is what you get from ket 0. A dagger acting on ket 0. A dagger acting on ket 1 gives you root 2 times ket 2 and so on. But we don't really need to go any further. Notice that the original ket beta had a B naught. That state is no longer there in A dagger acting on the ket beta. Since A dagger raises eigenvalues or number eigenvalues, the ket 0 has changed under the action of A dagger to ket 1. So this one has no ket 0 component, and that tells you that this state can never be equal to beta times this state, because this will have a ket 0 component. The raising operator, unlike the lowering operator, has no eigenstate. And that may seem a bit strange because, after all, if we have to do this in the position picture, all that changes is I in the differential in front of this d hat operator changes to minus I. So you get a similar looking differential equation, just the same kind of equation that you had for the lowering operator. Why then does this not work? The answer is, if you were to solve this equation, you will again get a very similar looking solution, or you will get something which has e to the power x minus xi0 whole square with a positive sign, which means that the wave function which satisfies this eigenvalue equation will not be normalizable, will diverge to plus minus infinity when you go very far away. Not a valid solution. So both from the position picture and just by looking at the action of the raising operator, we can see that the raising operator cannot have an energy eigenfunction. So the eigenvalue question has been answered. Lowering operator has energy eigenfunctions which are coherent states. The raising operator does not.